Okay, so this is question number 3 from the midterm. And in this question, we are given a set consisting of numbers from 0 up to 9. And we are given a subset of this set. And we are defining a relation on this set. Now, first of all, you have to make sure you really understand the domain of the relation. So this is the power set of S. So the relation is not defined on the set S, but rather on its power set. Okay, this is very important to understand. Define the relation R on the power set of S in this way. So I'm going to look at the definition later on, but let's first make sure we understand the structure of this relation. Now, this relation R is not on S. So the ordered pairs are not going to be like, for instance, 2, 7, or 0, 9, or 1, 5. So these are not going to be the ordered pairs we will come across in the relation R. Instead, the power set of S is the carrier set. Okay, so the power set of S would be the empty set and then the singletons up to 9. Then the subsets with 2 elements, 0, 1, 0, 2, up to 8, 9. And then comes the ones with 3 elements, 0, 1, 2, 0, 1, 3, and so on, 7, 8, 9. And then the 4 elements, 5 elements, up until S itself. Okay, so the relation R is on this set. The domain of the relation is this set. So my ordered pairs are typically going to look like, for instance, 2, 5, 7, 8, and let's say 1, 3, 9. This is a typical set and typical ordered pair that could appear on a relation on this set. Okay, so you have to understand what the elements of the relation could be and cannot be. So it could be something like this, but it cannot be something like, for instance, 8, 5. Okay, this is quite important. Now, let's look at the definition of the relation R. Okay, S1 and S2, they come from this set such that the intersection of both with T are the same. So for instance, this one, let's check whether this ordered pair is in the relation R or not. So what I need to check is the intersection of this subset with T. So this intersect with T, which is 2, 3, 7. What do I have? 2 is here, 3 is not, 7 is here. So this is, the intersection is 2, 7. So what about this? I don't have 2, I have 3, I don't have 7. So the intersection of this with T is 3. And this are different. Therefore, indeed, this ordered pair is not in the relation R. Okay. Now, so that's relation R. The ordered pairs will be consisting of subsets that have the same intersection with T. So that means if one does have 2, the other also must have. If one doesn't have 2, the other also cannot. And if one has 3, the other also must have 3, and so on. Okay, so that's the idea. Now I'm going to clear all these. And we want to show that this relation is an equivalence relation. And for that, remember, we want 3 properties. So number 1, we want reflexivity. Number 2, we want symmetry. And number three, we want transitivity. And I need to show that relation R satisfies all these three properties. So reflexivity, remember what reflexivity is. I want all pairs such that the ordered pair has the same two elements. Okay, so I want, let's say S1, S1, S2, S2, dot, dot, dot. So I want all of these pairs. And therefore, the question is every subset in the power set of S related to itself through R? Let's say an arbitrary, let S be an arbitrary subset of S, capital S. Okay, then since S intersection T is equal to S intersection T, trivially, S and S ordered pair is an element of R, and therefore R is reflexive. I'm just looking at the definition. Next, we have symmetry. So how do we show symmetry? If I have S1, S2 in the relationship R, in the relation R, I also want S2, S1 ordered pair also in R. So let S1, S2 be in a power set of S. And then since S1 intersection T, if S1 intersection T is equal to S2 intersection T, then I can obviously swap this. S2 intersection T is equal to S1 intersection T, meaning that if S1, S2 is in R, then by definition, S2, S1 must also be in R. If this is satisfied, this is obviously also satisfied, and so on. So symmetry is also shown. Finally, I need to look at transitivity. Now here again, let S1, S2, S3 be in the power set of S. Then if S1, S2 is in R and S2, S3 is in R, this means S1 intersection T is equal to S2 intersection T due to this ordered pair. And also, due to this ordered pair, S2 intersection T is equal to S3 intersection T, which means, well, this is equal to this in return, which is equal to this. So this means S1 intersection T is equal to this S3 intersection T. Therefore, S1 intersection T and S3 intersection T are the same. So by definition, S1, S3 ordered pair is also in the relation. Okay, and then we are done. So you have reflexivity, you have symmetry, you have transitivity, which means relation R is indeed an equivalence relation. In part B, we would like to describe the equivalence classes. Remember, every equivalence relation partitions the domain into equivalence classes. Now, what would they look like in this case? Describe the equivalence classes. So if S1 and S2 is in the relation, then that means their intersections with set T are the same. And as I said earlier, if S1, for instance, has 2, it will appear in the intersection of S1 and T. And therefore, it also must be in S2. Or, on the other hand, if S1 doesn't have 2, then the intersection will not have 2, which means S2 cannot have 2. Okay? So that means in terms of the elements 2, 3, and 7, all related subsets must behave the same. So if one has 2, the other also must have. If one has 3, the other also must have 3. If one has 7, the other also must have 7, or vice versa. If one doesn't have 2, the other cannot have 2, and so on. So this means in terms of the presence of 2, 3, and 7 in the intersection, we have 8 choices. None of them appear in the intersection. 2, 3, and 7 are not in the intersection, S1 intersection T, which means S1 and S2 doesn't have 2, 3, 7. So there are the subsets which doesn't have 2, 3, 7. So you should see where this is going. There will be 8 subsets, or 8 equivalence classes rather. So the intersection, if it is empty, then here you'll have like the empty set 0, 1. You don't have 2. You don't have 3. You will have 4, 5, and so on. 6, and not 7, and 8, then 9. And then you have the ones with 2 elements, 3 elements, up to a possible of 7 elements. So 0, 1, no 2, no 3, 4, 5, 6, no 7, 8, and 9. Okay? So in total, there will be, in this equivalence class, 2 to the power 7 subsets. Then here you can have just 2, just 3, just 7, 2, 3, 2, 7, 3, 7, and finally 3, 2, 3, 7. So here you'll have the ones like 2, then is 2, 0, 2, 1, 2, 4, 2, 5, dot, dot, dot. You don't have 2, 3 because it will appear here, and so on. Again, this will have 2 to the power 7 elements, and here you'll have 3, then 0, 3, 1, 3, no 2, 3. You skip that one for this, then 3, 4, 3, 5, and so on, and then the one with the 7 elements here. 0, 1, 3, 4, dot, dot, dot. So you will exclude 2 and 7. Okay, and then here you will have like 7, 0, 7, 1, 7, 2, 7 you have to skip because it will appear here. 3, 7 you have to skip, it will appear here. So then 4, 7, and it goes on. Okay, and then here you will have 2, 3, 0, 2, 3, 1, 2, 3, 2, 3, 4, dot, dot, dot. Here you will have 2, 7. You can't have 2, 3, 7. That will be here. But you will have 0, 2, 7, 1, 2, 7, 2, 4, 7, 2, 3, 7. You have to skip, it will go here, and so on. And 3, 7, 2, 3, 7 again. So you will group the subsets of S in terms of whether they have 2, 3, or 7 in them in 8 different equivalence classes. Each of them will have 2 to the power 7 elements, And in total, you'll have 2 to the 10 elements. And therefore, each equivalence class has equal number of elements, which is 2 to the power 7. When you add them up, all 8 equivalence classes, you will have a total of 2 to the power 10 elements, and none of them are overlapping. That's important. So this is a partition of the power set of S. Okay, let's look at question part C. How many elements does each of the equivalence classes have? Well, we have just gone over this, 2 to the power 7. And how many equivalence classes are there? 8. How can you explain this number? This is actually 2 to the power 3 because, well, this is the number of subsets of T, 2, 3, 7, because they also define the equivalence classes in terms of whether you have 2 or not, whether you have 3 or not, whether you have 7 or not. So there are 8 total possible possibilities, and therefore 8 is the number of equivalence classes.